Thanks. Yeah, my name's Isaac, and we're going to be talking about expanding physics reach with unused tracks in Lhcb. So just to give an overview of the Lhcb detector, in case you've forgotten, it's a general purpose single arm forward spectrometer with a pseudo rapidity in the range between 2 and 5. It was optimized for the study of particles containing B or C quarks, but its physics program has expanded beyond this a lot. It's got 3 tracking subdetectors, which are the Velo, located around the beam spot, the TT, which is located before the magnet, and 3 tracking stations after the magnet. It's also comprised of 2 rich detectors for the ID, as well as the calorimeters and muon stations. They've all been upgraded to run 3. And the tracks in Lhcb, these are reconstructed from segments in the different tracking subdetectors. And we give them different categories according to where they have hits. So you've got the Velo tracks, which only have hits in the Velo. You've got the upstream tracks, which are in the Velo and the TT. The downstream tracks are in the TT and the tracking stations. Long tracks have hits at least in the Velo and the tracking stations. And T-tracks only have hits in the tracking stations. So far in Lhcb, only long and downstream tracks are used for physics analysis, which limits the maximum decay length to around 2 meters. This is because they are better measured. And standalone T-tracks have not previously not been used for physics analysis. They've been overlooked. So why would we want to use them? So there's good motivation. So Lhcb was designed to study particles which decay upstream of the magnet after just a few picoseconds. However, it is possible to reconstruct particles with a larger decay flight distance using only T-tracks. But up to now, this hasn't been done. And the main reason is because there's reduced magnetic field in this region, which leads to reduced momentum resolution. Reconstruction of these particles would extend the physics reach of Lhcb in 2 main areas by allowing standard model and beyond the standard model long-lived particle analysis. Mainly the measurement of electric and magnetic dipole moments and searches for BSM long-lived particles. So we zoom in on the electric and magnetic dipole measurement possibilities. So these can be measured by exploiting the spin precession of particles that pass through the magnet before decaying. And this requires 2 things in particular. So the first is a source of polarized baryons that are not aligned with the magnetic field. These come from weak B and C baryon decays. And it also relies on a sufficient reconstruction of decays after the magnet, which require reconstruction of particles from T-tracks. As an example, it's already been shown that the lambdas produced in lambda B decays are maximally polarized. And this would be, these types of analysis would be interesting because sources of CPB in the standard model predict minuscule electric dipole moments. So these are sensitive to new sources of CPB and BSM physics. And the lambda baryon EDM was last measured 40 years ago. And with run-through data, we could improve the limits by 2 orders of magnitude. Also, the magnetic dipole moment measurements of the lambda and anti-lambda baryon provide a direct test of CPT symmetry. As for BSM LLP searches, so LLPs are present in nearly every BSM theory, and Lhcb is well suited to search for LLPs produced in B and D hadron decays. In particular, be able to reconstruct hadronic signatures, so decays to, for example, to pions and kaons, in addition to muons and jets. So far, searches in Lhcb have only used long tracks, and this means that the searches have been limited by the size of the Velo subdetector around the beam spot to around 30 centimeters. But if we do analysis with tracks made exclusively from hits downstream of the magnet, particles decaying up to 7.6 meters from the interaction point could be reconstructed, which corresponds to a lifetime of around a few nanoseconds. And you can see this in these plots. So these are produced by a summer student, Diego Mendoza, and they show the reconstructability of hidden Higgs decaying to a dimuon pair. And you can see on the right, reconstruction only with T-tracks would extend the lifetime up to over 500 picoseconds to a few nanoseconds. And you can see a real complementarity between using all the different track types to see a full range of lifetimes. And so can we do this, and why is it difficult? So feasibility studies have been performed using 2 standard model benchmark channels, run-2 data. We've got the lambda B to J psi lambda, with the lambda decaying to a proton and a pion, and B to J psi K short, with the K short decaying to pi pi. And we only reconstruct where the lambda or K short decays downstream of the magnet. And by reconstructing a prompt J psi to mu mu with long tracks, a kinematically constrained fit of the whole decay can be performed. But there are 2 main challenges to address. So first is extrapolating over several meters through an inhomogeneous magnetic field. But this can be overcome using a 5th order Ranchi-Kutta extrapolation, which is already present in the Lhcb framework. And the other challenge is the reduced momentum resolution due to magnetic field strength. And so to overcome this, we developed a multivariate classifier, and BDT, as well as using the Armenteros-Podolansky technique to improve the selection performance and mitigate cross-feed from other long-lived decays. And you can see some of the performance here. So the top left sort of shows that what one of the problems we're dealing with. So the mass peaks of the lambda and the K short are overlapping, so it's not possible to distinguish these between mass cuts. And that's down to the lower momentum resolution. We don't have particle identification available in run-2 for T-tracks. And you can see in the plot at the bottom, you can instead use the Armenteros-Podolansky technique to identify and separate somewhat lambdas from K shorts. Here you can see the momentum resolution. You can see that it's the proton and ion coming from lambdas. You can see it's improved by using the mass constraint fit, the decay tree fitter with the masses of the lambda and the J psi constraint. For protons, you can see it's a factor 3 improvement, and for ions, you can see it's a factor 2. Here you can see the efficiencies with the different selection criteria calculated with respect to the reconstructable particles, so those within the acceptance. One of the main issues that we have here, you can see, is the low vertex reconstruction efficiency. For this, we're investigating remedies. And here you can see some initial results on some preliminary results on data. So they're the invariant mass distributions with the lambda to p pi on top and the lambda b to J psi lambda at the bottom. After all the selections, this is after all the selections have been applied, including the BDT, the Armenteros-Podolansky beta, and the B-meson mass veto and the decay tree fit. And you can see that we get mass resolutions of 8 MeV and 41 MeV respectively. We're just going back to the vertex reconstruction issue. So it becomes more challenging the farther the decay vertex is from the tracking stations. And part of this is because of the low Q value in the decays, which means there's a small opening angle between the tracks. And this means that the tracks can cross twice within the resolution, which creates an additional ghost vertex, which you can see in the plot at the top there. This can be partially identified using this horizontality, which is defined as the sign of the proton times the magnet polarity times the unit vector of the decay plane in the y direction. And looking to the future, what do we have for run 3 and more offline analysis? So the Lhcb has undergone an upgrade for run 3, which includes new trackers, new vertex detector, and electronics. So we've got a new Velo, and the TT will be replaced by the U2, and the tracking stations have been replaced by the Sci-Fi tracker. That includes a fully software-based trigger, which will operate at a rate of 30 megahertz. And the HLT1 includes a reconstruction on GPUs. So the trigger is quite versatile and adaptable, allowing for the real-time analysis of events, and works well underway to include reconstruction with T-tracks in the trigger, which will help to improve over the run 2 feasibility studies, in particular by including PID information, as well as optimization of Kalman filtering for T-tracks. And we're also investigating the optimization of the vertexing. By including dedicated trigger lines, we can expand the physics reach of Lhcb. We're starting first with the benchmark channels, but plan to expand, including BSM LLP searches. Also looking into the possibility of using running T-track lines on the HLT1. And so here's just a very preliminary plot showing that in run 3, it shows the difference in log likelihood between the proton and pion hypotheses for true proton and pion T-tracks, associated rich info. And it shows that we'd be able to get an acceptable separation between the two by applying cuts, for example, at 0 or at 5. And future plans for offline analysis. So we want to expand use of PID. So including from rich to the muon stations, also looking at expanding use of the Armenteros Podlansky technique. We expect to expand use of multivariate analysis and machine learning techniques to try and optimize our selections as well as the vertexing. And we're investigating sensitivity and analysis for the EDM and MDM measurements as well as DSM LP searches. And we're also looking at ways to further improve the momentum resolution by including information from the other subdetectors downstream of the magnet. So just to summarize, the physics reach of the Lhcb can be extended by reconstructing particles decaying downstream of the dipole magnet, which permits electric and magnetic dipole measurements. And this can significantly extend the reach of LLP searches as well. And this has been demonstrated already on run 2 data with a paper to be released in the next few weeks. And we're excited to bring new results as run 3 gets underway.
Thank you. I will just check on Zoom if there are questions there. In the room.
Hi, okay, you mentioned the physics motivation, but there on the T tracks, there is no way just to identify pions, protons.
So not in run 2, because the information wasn't saved, but starting in run 3, we should be able to add the switch to PID information to identify protons. It's a very preliminary.
Which information are you using? Is that rich?
Yeah, so that uses rich 2.
But it depends whether the decay is producing, right? So if the decay is after the rich, there is no way you can identify.
Oh no, yeah, but if they were after the rich, that also be after the tracker. So we don't use the rich 1 info, it's only using rich 2, it's only the rich 2, which is after the Sci-Fi tracker, which is included.
Okay. You mentioned that you have enough resolution for the momentum, but with such low B field, is that really possible to get the narrow mass? You were quoting something like 40 dB.
Yes, I think that's including the the decay tree filter constraint. So I think that really helps to bring it, to improve it quite a lot. So it's using, for example, the JSI to Mumu, which is reconstructed with one tracks, and so that's coming from the positive primary vertex, and that really helps to improve the momentum resolution.
Isaac, for the improvements you have shown, the plan improvements, the Kalman filtering is also planned to be run fully on the GPU. On this, don't know.
I don't think so. I think that's
No.
It's all CPU. I mean, it's all H52 registered for this.
I see. So I would have advertised the coffee library for the magnetic field if you wanted to use that at least to see.
Or you can anyway advertise them.
Yeah.
You have to try this.
We're trying to gain some other users if they can if they experience that is a good thing. Yeah. Okay. Then let's thank Isaac again.